The universe is a canvas stretched by dark energy, painted with a background of dark matter, and splashed with the light of 100 billion galaxies. It would seem to be enough for anyone, but cosmologists have speculated about regions of space-time inaccessible to us, because they're completely separate. This is beyond the expansion that is known to have carried regions of our universe beyond our view, or beyond our horizon. This is the idea of completely independent spacetimes. The concept is called the multiverse. To talk about the multiverse, we reach the frontiers of knowledge and cosmology. We also consider a metaphor called the Ouroboros, the snake that eats its tail. This ancient symbol, found in many world cultures, symbolizes in physics the unification of the very small and the very large. As we've seen, it's possible that the tests of fundamental theories of matter will involve observations of the very early universe. And the ultimate theories of nature can only be tested there. Humans, in the Ouroboros, this realm of orders of magnitude, happen to lie in the middle of the logarithmic range of scales, from subatomic particles like quarks to the visible universe. The basis for talking about the multiverse is the fact that there's more to space and time than we can see with our telescopes. It's easy to find galaxies in the universe who, when their light was emitted, were moving away from the Milky Way at faster than light speed. As we've seen, the microwaves from the Big Bang were actually generated when any 2 points in space were moving apart more than 50 times the speed of light. So it's a completely conventional part of the Big Bang model that the space-time that exists is more than the space-time we can see. The multiverse idea goes further and speculates that the universe was a quantum event. The genesis came from random quantum properties that might be a part of a suite of other quantum events, other universes. The inflation idea puts meat on the bones of the multiverse. Because if inflation happened, when we look at the speckles in the microwave sky, we are looking at quantum fluctuations expanded to the size of the seeds for subsequently forming galaxies. The quantum universe is going to be a strange place, difficult to understand. As Richard Feynman, the famous Nobel Prize-winning physicist, said, anyone who claims to understand quantum theory doesn't understand it at all.
It upset Einstein very much, you know. All that damned quantum jumping. It spoiled his idea of God, which I tell you frankly is the only idea of Einstein's I never understood. He believed in the same God as Newton, causality, nothing without a reason, but now one thing led to another until causality was dead. Quantum mechanics made everything, finally, random. A thing could be this way or that way. The mathematics deny certainty, they reveal only probability and chance. And Einstein couldn't believe in a God who threw dice. He should have come to me. I would have told him. Listen, Albert, he threw you. Look around. He never stopped.
We're entering the realm of mathematical cosmology. It's always been puzzling, even mysterious to physicists, that mathematics describes so beautifully the universe. This was a point made by Einstein in his general theory of relativity, a beautiful set of second-order partial differential equations that seems to describe the behavior of the entire universe. It's also true in the multidimensional geometry that underlies string theory, beautiful mathematics in its own right, whether or not it has any application to the real world. We can imagine, therefore, levels of reality that we might be able to inspect with science. The first is the fact that the model tells us there are regions in the Big Bang model that we cannot see. The second level, the multiverse, is that if the universe was a quantum event, there may be other universes, bubbles of space-time if you like, that are unobservable by us, all beyond our horizon. The third level of this is the unpredictable nature of quantum genesis. and the other possible universes, since they're governed by the indeterminacy of the quantum theory, very hard for us to predict. Perhaps an ensemble of behaviors can be predicted, but not the behavior of any individual quantum event. The final level is pure mathematics, the description of space-time, perhaps in multi-dimensions beyond the 3 of space and 1 of time that we know, the pristine beauty of mathematics that may or may not apply to the real universe. String theory is the working canvas for the multiverse model, because string theory predicts that the vacuum is rich with Byzantine possibilities. Quantum events can occur in string theory with enormous range in their physical properties. When string theorists calculate the number of possible states of the vacuum, they come up with a prodigious number, 10 to the power 500. That's an unimaginable number, and even if almost all of those vacuum states don't ever emerge into a real universe or something that could be observed or has macroscopic size, if only a tiny fraction do, then it's a rich set of possibilities for a multiverse model. Inflation is something that we believe happened to our universe in the first tiny fraction of a second. But in the eternal inflation idea, similar things could have happened to other bubbles of space-time and could have inflated them into large universes like ours. So we have a speculative physical basis for an ensemble of universes with randomly different properties. By different, I really mean different. The laws of physics would be different in these spacetimes. Some similar to our laws of physics, others different. Perhaps some universes where the arrow of time was not discernible and events move forward or backward with equal facility. Perhaps universes with equal amounts of matter and antimatter. Perhaps universes that live and die in a microsecond, or universes that are more eternal than ours. We don't know, but what's clear is that the set of properties in our universe that enables life to exist, biology, humans, is quite special because we need long-lived stable stars, molecules, chemistry, and then biochemistry to develop. If you look through all the possible parameters and laws of physics that could exist, only a small range of these laws of physics will accommodate our kind of universe, the one that holds life. This logic is called the anthropic principle and says that our universe does have special properties in an ensemble of possible universes because the vast majority of them will be stillborn, in the sense of not accommodating complexity as exemplified by biology. The speculative frontier of cosmology is a concept called the multiverse. It's born of the idea that our universe had a quantum genesis. That's part of the inflationary cosmology that has some verification from observation. But it goes beyond that to speculate that out of one quantum event there may have been many, creating spacetimes with different physical properties and even laws of physics unobservable by us. Because they're unobservable, testing the multiverse theory may be extremely difficult, but some theorists think it might be possible. It's extraordinary to consider that our universe contains 100 billion galaxies and is 90 billion light years across, yet may not be all there is.